So dollar display means it will print the immediate value. Suppose whatever the display statements we are taking, for example, we already seen some of the codes, right? So where dollar display can be used. So we'll see some programs. Suppose I am taking module display statement. For the display statement, we can write some variables like reg variable. Reg variable is of the 3 or 4-bit size. Okay, some variable name is some address and initial begin some address equal to 20 or address equal to 8 because within the range 4-bit range we can take, right? So I'm doing dollar display here. Suppose dollar display address equal to percentage d in decimal we can represent comma address. So again at the hash 5 time units, I'm changing address equal to 5. Again dollar display, I'm taking here with the time mentioning time dollar time. Dollar time is a system task which represent the current simulation time, right? We already discussed. So here we are ending and module. So this is the dollar monitor, sorry, dollar display. So you can run the program. So what is the value? So at 0 simulation time, address equal to 8. At 5 simulation time, address equal to 5. Suppose if you take again at some simulation time, again you are taking address equal to 10. At 10 simulation time, again the dollar display value will be printed address equal to 10 at 10 simulation time. Okay. So that is about the dollar display. In place of dollar display, see, if you observe, suppose if you want to print all these three changes of the input, you need to write 3 times dollar display. Okay, so it will print only immediate value only. Suppose at 10th line dollar display, I am commenting it. Okay, so will it print all the three statements? You can run the program. See, it doesn't print the address equal to 5 because dollar display is not mentioned there. Okay, dollar display means it will print only immediate values. Wherever you taken there, that values, that variables only, it will print. Okay, that is the dollar display. Suppose in place of dollar display, I want to use the dollar monitor. So by using the dollar monitor, it will print every change of value, for the variable. Suppose, sorry, dollar monitor. So you can run. So see here, every change of the value, it got printed. Okay, no need to write those many times. Only one time is enough. Dollar monitor is enough for one initial block one time. Okay, so 0
Ma'am, so
address
we,
equal to 8. All the three statements 5 at 5 time units address equal to 5 at 10 time unit address equal to 10, all the variables got printed. Okay, so that is the need of dollar monitor, no need to mention every time. Okay, yes, tell.
ma'am, so dollar monitor we have to add at the beginning of the like at the
At the
starting of the line
beginning
or
or at the beginning or ending, anywhere, no problem. Okay, it will monitor every value. Okay, mostly sometimes it will give accurate result for the beginning only. In my observation, like whatever I have observed, if you write beginning, then only it will give you the best result sometime. Otherwise sometime it doesn't give any value. Okay, so you can just try by putting middle of the code and ending of the code. Okay.
Okay.
Okay. Dollar display, dollar monitor. Everyone understood about dollar monitor?
Yes, ma'am.
Okay, so in place of dollar display, I'm putting another one is a dollar write. So what is the difference between dollar display and dollar write? Means if you see display, one statement after another statement is printing one by one, line by line. Okay, taking new line. But whereas a dollar write, it doesn't take the new line. Dollar write means it doesn't take the new line. All the statements will execute in a same line. Dollar write. So if you see 0 simulation time, address equal to 8, 5 simulation time, address equal to 5, at 10 simulation time, address equal to 10. Okay, same as a dollar display only. If you don't write, if you comment here, that particular value, it doesn't print. Dollar write also print immediate value only, same as dollar display, but it doesn't add the new line. See, only two statements are printed. Okay, so same as dollar display only. Suppose if you want to put, if you want to take the variables, if you want to add the next line by using the dollar right. So how can we add means simply you can put here the black slash new line. That mean it goes for the next line, right? For it represents the next line, right? So like that you can put backslash not this new line. Okay, so that it will add the new line for that particular statements. Once it printed for the next statement, it will go to the new line. Okay, like that. Suppose if I put for all, so one by one will be printed. Okay, so that is the difference between dollar display, dollar monitor, and dollar write. Next thing is dollar strobe. So what is the dollar strobe? Dollar strobe means it is also a display simulation, it is also display the values. Whatever the current simulation time value is there, that value will be displayed. Okay, suppose I am taking in this example. Suppose I am taking at 0 simulation time address equal to 8. In this place I am putting dollar strobe. Okay. And same here I am taking dollar display also. Take this dollar right and put here dollar display. And here I am taking address equal to 5. At 0 simulation time, address equal to 5 I am taking. Okay. So just remove these two things. Can you tell me what will be the output for dollar strobe and what will be the output for dollar display?
Ma'am, for dollar
Dollar
strobe,
stroke 5
5, and for dollar
and
display,
dollar display 8.
Yes. So dollar strobe means it will print the current simulation time value. See, for dollar display it is a 8 and for 0 if you want to understand clearly write here for strobe. First this is the strobe address and this is the display address and this is also strobe or display. Here we need to write strobe, or you can just remove this thing, no need to write this. Okay, now run. Okay, see, first dollar display has printed is equal to 8. Even strobe before value is address equal to 8. But at the current simulation time, there is another value also, address equal to 5. So, strobe address equal to 5. This is the difference between dollar strobe and dollar display. Okay,
ma'am,
everyone
so
understood?
ma'am, so
Yes, tell.
strobe will basically take the variable which we have initialized and will go through the entire test bench and will give the current value of the variable, ma'am.
Yes, yes. If you go to entire test bench, suppose hash 5, address equal to some 10. Okay. So here also same, if you put dollar strobe and dollar display, what will be the values? What
Ma'am,
will be
for
the value?
ma'am, for dollar strobe it will be 10 and for dollar display it will be also 10, ma'am.
Okay, so what about this dollar strobe value?
Ma'am, 10.
This one, first dollar strobe value. For this dollar strobe, current value is address equal to 10. Okay. Uh, for this dollar strobe, current value address equal to 5. That value only it will be printed, right? Okay, see, if you observe, first dollar display equal to 8, again dollar strobe equal to 5, dollar display 10, again for strobe current value is 10. If you take same whatever here I have taken address equal to 5, if you take
Excuse me,
same
ma'am.
here, that mean
Ma'am,
both this address equal to 10 and this address equal to 5 are executing at 5 time units only. Then what is the strobe value here? I will take another value. What is the strobe value here?
ma'am, can you please mute everybody?
See, I'm telling dollar strobe means it execute at current simulation time, whatever the current simulation time, the value is there, that value. So here first strobe is there, the statement, wherever the statement is there, whether it is in a first line or second line, whatever. So here what is the current simulation time is a 0. At 0 simulation time, what is the value of address? Last value is 5. Okay, so that you observe. If I don't take this address equal to 7, then what is the value of this strobe? Last simulation value at 5 time units is 10, right? So if I add address equal to 7, then what is the last simulation value here for this strobe statement?
Ma'am, 7.
7. How?
Ma'am, because that at
5
the
is
current
executing, address equal to 10. At this 5 time units only, here also address equal to 7. So value is 7. If I run there, the strobe value is 7, display value is 10. See here, strobe value is 7, display value is 10. Okay.
ma'am,
Kirti, you got clarity now? Last
Yes,
session
ma'am.
you didn't got clarity, right?
Yes,
Okay.
ma'am. I also tried it on one example and got it.
Okay.
ma'am, so dollar strobe and dollar display is basically at the current time, like for the zero simulation time, whatever current value is there, it will print. And
Not at
for
zero simulation time or whatever the simulation time. Dollar display means it prints immediate value. Whatever the time, whatever the value is there, it display the immediate value. Here its immediate value is 8. Okay. If I put dollar strobe, okay, don't confuse. I'm just removing these things and I'm putting here now. Okay, dollar strobe and dollar display. So previously what values it printed? Dollar strobe equal to 5, dollar display equal to 8. But now both will be 5 only. Okay, so we'll see like this.
also, ma'am, can you please mute everybody because there's a lot of background noise.
Okay, now see here, address equal to, here display equal to 5 and strobe also 5. Okay, but here address for display statement address is 10, for strobe is 7. Everyone got clarity now?
Yes, ma'am.
Okay, clear? Any doubts?
Ma'am, coming to difference between display and write. Other than that,
Display.
difference. I mean, dollar
Other
display
than
and
that, no
dollar right.
difference is there. Dollar display and dollar write both are same, whereas dollar write doesn't add new line. Dollar display add new line. Okay.
Ma'am, can you please copy paste this code in the chat, ma'am?
Okay. Okay. Next thing is a dollar dump fare and dollar dump file. We already discussed and we'll discuss now in the examples. And next one is dollar finish, which is used to terminate the execution, and dollar stop. Dollar next today we'll discuss how to model different types of combinational logic circuits. Okay. Tomorrow different types of sequential logic circuits. So today we'll discuss how to model different types of combinational logic circuit. Okay. So we already seen how to model the different types of multiplexers, right? So in behavioral modeling, we have seen in the data flow modeling or in gate level modeling, like that we have seen so many models, right? So have you remember how to write in behavioral? You can use if else statements, or you can use like assign statement. Okay, assign condition, assign expression using assign statement can be used only simple examples like 2 by 1 multiplexer or 4 by 1 multiplexer. But if you move to 8 by 1, 16 by 1, that is very complex. Okay, so for complex multiplexers, if there is a 32 by 1 multiplexer, there are 32 number of inputs. So that time, how can you represent?
I'm using
How can
vector
you
or array model.
represent? You're using vector variable. Okay. The code logic, how you will write the code logic?
So, ma'am, first we will suppose we have to make a 16 is to 1 mux. So for that we have 4 select lines. So we will initialize a vector of 3 is to 0 to for the selection lines, and 15 is to 0 for the input. So simply we assign a statement that is assign out equals to out of in of select, that will simply assign 16 is to 1 mux.
Any other answers? Okay. Any other answers?
We can use a generate. We can generate a loop and call a single multiplexer with.
Hmm. Okay, we can use generate block genvar keyword. Tomorrow we are going to see that genvar, how to use that. Okay. Any other answers? Can you please join for the session again? Can you please join for the session?
Yes, ma'am.
Okay, I understood, Fanish, what you tell. I understood. We'll discuss.
Ma'am, just before you end the session, can you please just tell what's the t variable representing over here?
Where?
Ma'am, eighth line.
Eighth line here. T in the sense
It's just a wire variable. Okay, got it.
wire variable between multiplexer connections. This is 4 by 1 marks using T by 16 by 1. Sorry, 16 by 1
Okay.
marks using 4 by 1. So that is
Ma'am,
internal variable.
can you please copy paste the code as well?
Wait, the session is completing. It's less than 1 minute. Join again. If you see, there are complex multiplexer. Okay, this is the multiplexer which has inputs 32 number of inputs. Okay, and 5 selection lines and 1 output, or otherwise 2 power n number of inputs, n number of selection line, and 1 output. Okay, whenever the number of inputs are more complex, okay, whenever number of inputs are increasing, so how can we design the multiplexer? By using if else statement. Okay, by using case statement, it is very difficult to do the programming, right? For those many lines. So multiplexers, full adders, decoders, encoders, these are basic things. Shift registers, counters. Okay, everywhere we will use these things. Okay, every program, I mean every project, every protocol these things are very small things. Okay, so that time whenever we are designing complex projects, complex protocols, whenever these types of small block is involving, we need not to spend more time on these small blocks. Okay, whatever the code, how simplicity we can write the program, that is very best thing. Okay, for that also we cannot use if else blocks, case, on all these complex things. Okay, as simple as possible within a single line we need to end the program. Okay, so for the multiplexer, there is a small trick we can follow to write any size of multiplexer using a single line. Okay, that is, suppose how the multiplexer will be work based on the selection line only. Whatever, if selection line is 0, zeroth line of the multiplexer, whatever the value is there in zeroth line of the multiplexer, that value will be assigned to the output. If selection line is 1, the first line, whatever the data is there in first line, the data will be assigned to the output, right? So how can we put that thing? So selection of input. Selection of input means input maybe 0 or 1 or 2 or 3, anything, any value. Okay, so selection of 0, sorry, not selection of 0. We are not sending the data of selection line value, right? We are sending the data of input of select. Okay, that means if selection line is 0, whatever the data is there in 0th location, that data is going to assign to the output. If selection line is 1, whatever the data is there in first location, that means first value, that data is going to assign to output. Okay, so by using this simple statement, we can design the multiplexer, any complex multiplexer. Okay, so if you see here it is the 2 by 1 multiplexer. If it is not 2 by 1, you can take either 4 by 1 or 32 by 1, anything. Okay, so input, here we have taken 16 to 0, that means 16 bit, sorry, 15 down to 0, that is 16 bit. So 4-bit selection line and 1 output. So what is the statement we have written? Input of S equal to output. Okay, so if you write, so here we are writing 16 number of combination. You, in place of 2, you can put directly 16 by 1 marks. Here also DUT 16 by 1 marks. So what is the I we are generating? It is a 16-bit value. It is a 16-bit value, and selection line S is equal to some value, 5, at next 5 equal to some value, and again some, like this we are generating. Okay, by using the initial, you need to generate all 16 number of combinations like this. Okay, otherwise you can use always block. The some tricky things you can follow. Always at a hash 5, uh you can change like S not, always at a hash 5, S not is equal to complement of S naught. That means every 5 time units, this last value should change, right? Suppose there are 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, double 0, 0101, like that. If you continue, for every 5 time units it should change. Here 5 time units it should change. Here 5 time, here 5 time, every 5 time unit it should change. Every 10 time unit, here this value is changing, right? Every 10 time value, 10 time unit it should change, like that. Every 15 time unit or every 20 time unit, here every 40 time unit, this should be changed, like that. You can use some tricky things. So always set hash 5 as not equal to not as not, always hash 10 s1 equal to not s1, always hash 20 s2 equal to not s2, always hash 40 s3 equal to not s3, Okay, if you use these four statements, total 16 number of combinations can be generated easily. We can generate very easily. Okay, so yeah, this is how we can write the test bench. Okay, simply in Verilog. Okay, we'll see, we'll do the simulation and we'll check what is the output.
Ma'am, actually the test bench and design are interchanged, ma'am.
That's not a problem. Okay, we can change. So if input equal to 0, 1, selection line equal to 1, output equal to X. Why we got output equal to X?
Was in test bench we did S size line number 4.
Here I equal to 16, 15 down to 0 we need to take. S also 3 down to 0 we should take. Now run. So whatever the input based on the selection line. So what is the selection line here? 0, 0, 1. So you need to see how we have defined 15 down to 0. 15 down to 0 means from these, so this is the 0th bit, first bit, second bit, third, fourth, fifth, sixth, like that. If you take 0 up to 15 means the 0th bit will be started from here. 0th bit, first, second, third, like that. But here we have taken 15 down to 0 and selection line 3 down to 0, right? So selection line is 1. So what is the first one bit is 0. If selection line is 2, 0. If selection line is 3, 1. If selection line is 4, 0. So like this, by using the single assign statement, you can generate any size of multiplexer. Okay, clear everyone?
Yes, ma'am.
Everyone clear? Okay, so how can we generate hierarchical multiplexers? We already seen multiplexer for behavioral data flow. That thing you can practice. So how can we design hierarchical multiplexer 16 by 1 multiplexer using 4 by 1? So total there will be 16 by 1 multiplexer using 4 by 1 means 16 by 4 equal to 4. At input side it should be 4 multiplexers.
Output
So
one.
each multiplexer has 4 inputs. Here also 4 inputs, 4 4. And it should have two selection lines. So here selection line S0, S1, all are interconnected. So here another, no need to take two, right? One multiplexer
Only
is
one is
enough. One multiplexer is enough. So here is one, here is one, here is one, here is one. So here also we have two selection lines, S2, S3, and one output. So this is one 4 by 1 marks. This is one 4 by 1 marks, 4 by 1. So these all are I of 0 or whatever input, I of 1, I of 2, I of 3, like that. These are internal variables T0, T1, T2, T3, internal connections, wire connections. So this is the outer. So this is how we can design a 16 by 1 multiplexer using 4 by 1. Like that you can design 8 by 1 multiplexer using 2 by 1 marks. Okay. So how to write the program for that multiplexer? Okay. First, what we need to do? First thing we need to design one 4 by 1 multiplexer. By using this 4 by 1 multiplexer only, we can connect all the hierarchical connections, right? So first we'll design this 4 by 1 multiplexer. Okay, clear? Everyone understood? Everyone understood up to there?
Yes, ma'am.
Okay, see here, module multiplexer 4 by 1. D is the input selection line, Y is the output, 3-bit size and 2-bit selection line. Whatever we have discussed the previous program, same we have assigned here. Okay, assign Y is equal to D of select. This is one 4x1 multiplexer. Now, by using this 4x1 multiplexer design, we are going to make 16x1 multiplexer. That is calling as structural modeling. Okay, that is a structural modeling. So this is the module 16x1 multiplexer. Input is D, selection line, and output is Y. What is the size of D? It is a 15 down to 0, total 16-bit size, and 4-bit size S, and output is a single bit, and wire is a 3 down to 0. 4-bit, I have shown the internal wires T0, T1, T2, T3, which is coming out from 4 multiplexers, right? So that is the wire here. Okay. So how we can structurize here? So how many multiplexers are needed? Total 5 multiplexers, right? 4 here, and all these we are taking one multiplexer. So total 5 multiplexers. So multiplexer M1, multiplexer M2, multiplexer M3, M4, M5. Okay. Now we need to make the connections. So for first multiplexers, what are the inputs here? We have taken D as a input. So D as a input means here we'll have D0, D1, D2, D3. Okay. So for second multiplexer, D4, D5, D6, D7. Next, D8, D9, D10, D11. Next, D12, D13, D14, D15. So, same we have mentioned here, right? For first multiplexer, it is a D 3 down to 0. Next, what are the selection lines? S 1 down to 0. Next, what is the output? T of 0 is the output for first multiplexer, right? Like that, for second multiplexer, 7 down to 4 are the inputs. Selection line 1 down to 0, T of 1. For third multiplexer, 11 down to 8, selection 1 down to 0, T of 2, 3, like this. And for last multiplexer, what are the inputs? T of 3, T 3 of 0 is the input, S 3 down to 0, that means S2, S3 are the selection lines, and Y is the output. This is how we can write for hierarchical multiplexers or triple carry adders or carry look ahead adders. Wherever you find these hierarchical multiplexers or hierarchical blocks and all, we can design in this way. Okay, everyone
Okay,
understood?
ma'am.
Yes, tell.
Ma'am, so if we have written S2 is to 3, then it will be basically the same, right? Like S2 and S3 only, right? But it will
S2
be
is to
in
3. S2 is to 3 means how, see, S3, you need to follow one model. Okay, see, if you follow here 15 down to 0, 3 down to 0 means in test bench also follow the same thing. Okay, if you don't follow, if you write 3 down to 0 and 0 up to 3, in this case, what happens? Overall design will get wrong, right? Suppose here the selection line, if you take in this order 0, 1, 2, 3, here 3, 2, 1, 0, the order will mismatch and entire design will be get wrong, right? So here in this place, you need to take 3, 2 only, because 3, 2, 1, 0. These two we already connected there. If you these two we need to connect one multiplexer. If you connect in reverse, this 1 will come to here, this 0 will come to here. That will be entire circuit design will be wrong,
yes, ma'am.
right?
Got it, ma'am. Got it, ma'am. Got it, ma'am.
Yeah. So any doubts in the design part?
Ma'am, so let's suppose if there is a circuit where we have to connect S1 and S0 to the next multiplexer, and S3 and S2 to the first 4 multiplexers, ma'am. So in that case, we have to use 0 up to 3, and then 0 up to 1 and 2 up to 3. In that case, ma'am.
Yes. Yes.
Got it, ma'am.
Whatever the flow you are following here, follow same. Otherwise, the design output will get wrong. Okay. Try in different ways. You observe whatever the questions you are asking. try to observe in the program so that you will also understand, right? Okay, so see here, module TB, reg, you know this test bench and all, no need to explain. So here we have taken hash 5 equal to, with 5 units gap, we have taken all 16 number of combinations. If you don't want to take all 16 number of combinations, whatever we have used previously, by using the always, I will show you one example with the always also. Always hash 5 time units. What is that? S of 0, right? So S of 0 equal to not, S is small only, right? Okay, S, not S of 0. Like that, hash 5, here hash 10, hash 20, hash 30, sorry, 40. So here S of 1 should get, here also 1, here 2, here also 2, here 3. Did you all understood this logic, everyone? Instead of writing all these things, I'm just putting like this. So if you see see here, you observe here, same program. If you observe here, this is the S0, S1, S2, S3. So if, 0 is changing for every 5 time unit. So we have written that thing. S of 1 is changing for every 10 time unit. So same thing we have written. S of 2 is changing for every 20 time unit. So same thing we have written. S of 3 is changing for every 40 time unit, right? So 10 plus 10 plus 10, 40 time unit. So same thing we have written within 4 lines. Okay.
And ma'am, we are using always because we have to change that bit every 5 time even. It should be continuous. That's why we are using always, right?
Yes, because always is a loop, right? So that's why. Um, undeclared identifiers. Yes.
The teeth rod line it is coming somewhat green.
Ma'am, S should be capital, ma'am. S should be capital. Both side, ma'am. LHS and RHS.
Unexpected token at 13th line. Always at the rate of, always hash 5. Okay, we need to write outside the initial block. So here only dollar monitor is there, right? So initial dollar monitor. Initial begin.
I think we need to initialize the value of yes also to 0, 0, 0.
Ma'am, also the end statement you have added before the 16th line.
Before here for it's for initial begin. So here always loop should stop, right? It is not stopping. It is in like continuously. It is iterating, right? So initial
Finish. Dollar finish.
at hash 100 time units or 50 time units, you can use dollar finish.
Ma'am, can we use the same statement in the first initial block which we have used, ma'am?
Yeah, we can use there also. So at 100 time units, before 100 time units, it stopping simulation, right? So here 0, 0, all zeros in the sense, first bit is 0th bit is 1. All zeros, 0th bit is 1, next 1 bit, next 1 0. Like that, you can check this program. Okay, I will share these programs to everyone. So you can try yourself. Okay, so initially you need to put s is equal to all zeros, initialization with 0, so that it will generate here. Okay, so this is how we can write hierarchical multiplexer. Everyone understood there up to there?
Yes, ma'am.
Okay. Next one is how to write the full adder in a simple way. Like multiplexer, we have used one line, right? So how to write the full adder in a simple way. So this is how. Here we have taken input x comma y comma c and output sum and range always at the rate of inputs c out comma sum equal to all the inputs, addition of all the inputs. Okay. So by using always block, we have written this thing. No, if we already seen how to write the full adder in a gate level and
Ma'am,
data flow modeling.
can we write adder using the continuous assignment?
Continuous assignment, yeah. Here we have used continuous assignment. We can write like this also.
No, but
Otherwise, if
here
you
we are
don't
using
want to,
always, no, reg.
wait,
So
wait.
procedure. Yes.
This is a continuous. Okay, you're telling. Yeah, that's what I'm showing. Telling. So you can write with a continuous assignment. So see out, assign, see out, comma, sum equal to C in plus x plus y or y plus x. Y is the p. So y plus x. Okay. You can write simply here like this.
Okay.
It will also work.
So,
Okay. So next coming to the test bench. Module test reg wire full adder. We have
but when we
instantiated with full adder.
when
Hmm.
we synthesize this code, this will not generate any register in our RTL designing. But as a full adder, we need to synthesize a register so that it can able to store that value in it. But here it will generate a wire only. That's why I'm asking.
Where in always blocker.
Yes, ma'am. So I think only we can use always because when we use the
Here,
assign statement,
if you use this type of statement, if you use this also, it doesn't generate any gates or anything because we didn't written here in a gate level modeling, right? Just we have written in a simple expression. It doesn't contain any gates and all. So it doesn't generate any circuit.
Ma'am,
Simple
but
block.
but
ma'am,
ma'am,
Yeah,
in
tell.
the when we are using the procedural block, we are using the cout and sum as register. So basically,
Hmm.
when we synthesize this code, this will generate a reg in our RT designing. But as we are using assign here in the uh, data flow modeling, it will not generate any type of register. So is it correct?
Yeah, we can use actually combinational logic circuit doesn't have any registers, right? That is just coding style where we use always block. Okay, if you use always block for every combinational, it will generate some internal register, but it is not necessary.
Okay, ma'am. Okay. So basically, it's all depends on our coding style.
Yes, yes.
Okay.
Okay, these
Ma'am,
simple
but
things where we use means if there are multiple blocks are there, suppose if you take any architectural level, there will be some adders, multiplexers, registers, parallel in parallel out, serial in serial out. We need to convert the things, right? So there we can use these simple things without writing complex ways. Yeah, tell.
Ma'am, I didn't get the assigned statement, ma'am. 12th, like how did you
Hmm.
directly write the expression
Okay.
C in plus Y plus
See
X?
here, x is a 1, y is a 0, c is a 1. So what is 1 plus 1?
1 0, ma'am.
1 0. This 1 will go to carry c out. This 0 will go to sum.
Got it, ma'am.
Hmm?
Yes, ma'am, got it.
Have you got